So, section 10.1, day 2. And we're going to talk about permutations. Okay, so let's say we have something like 10 books to place on a shelf. Okay? And we want to know if we're putting 10 books on a shelf, how many different orders can we put those books on the shelf from left to right? So the idea is that we have 10 different spots on the shelf. How many different choices can we make for the first book on the left? There are 10 different books that we can put in that position. Once I put a book there, how many are left for the next one? And then what's another way of writing this? 10 factorial, and we talked yesterday about using the factorial under probability on your calculator. 10 factorial ends up being a rather large number. So it turns out to be 3,628,800 different ways of putting those books on a shelf with only 10 books. It's a lot of different arrangements. Each of those arrangements is called a permutation. It's a different order of those books on the shelf. Okay, everybody got that? So that's the idea of permutations. So it's an arrangement where order matters. So if I flip 2 books around, that's a new outcome. That's a new arrangement of books on the shelf. Now, what happens if instead of 10 books to place on the shelf, what happens if we have 10 books and we only want to place 4 of them? How many different ways can we put those on the shelf? Well, now instead of having 10 positions, we only have 4 positions. So do you guys see it's going to be 10 times 9 times 8 times 7? Right? 10 for the first spot, then 9 choices possible for the second spot, etc. We multiply those together using the counting principle. It's going to be a considerably smaller number, right? Only 5,040. So that's easy enough to do. But what happens if we have 100 books and we have room for 37 of them? And we want to know how many different ways we can put those on the shelf. Are we really going to want to put 37 lines and put 100, 99, 98, 97, 96, etc., 37 times? It's going to take us a really long time, isn't it? So there's a shortcut for doing this, and that is to use our formula for permutations. So it turns out that permutations how many ways can n things be arranged r at a time? In other words, how many ways can 100 books be arranged 37 at a time? That's the idea. And the symbol for that in general is NPR, where the P stands for permutations. Different orderings. And there's a formula for it. It turns out to be n factorial divided by n minus r factorial. Does that look kind of familiar from last night? You guys had things like 12 factorial divided by 12 minus 5 factorial. That's what they were doing, is getting you ready to use this formula. So for example, if we have 10 books and there's only room for 4, that would be 10 books chosen or arranged 4 at a time. That would be 10p4. We're only going to choose 4 out of the 10 books. This would be equal to 10 factorial divided by 10 minus 4 factorial. That's really 10 factorial divided by 6 factorial, right? We can do that on our calculator. 10 factorial divided by 6 factorial. Notice that gives us our same answer, doesn't it? Because what this is really doing, guys, is this is really 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. Remember we talked about this yesterday? These would cancel out and give us 10 times 9 times 8 times 7. Isn't that exactly the way that we did it here? But it's just a shortcut for doing that for us. Now, you want to see an even shorter cut? Your calculator has this on it. So if I pull up my calculator, notice next to my exclamation point, my factorial, I have an NPR choice. So if I want to punch in 10p4, I do 10 and then NPR and then 4 and hit equals, and it will do the formula for me. It's putting the 10 into the N place. It's putting the 4 into the R place. So you guys can find NPR. It's either going to be located above a button on your calculator, or it's going to be in your probability menu. If you keep scrolling to the right, past factorial, you'll eventually see NPR and NCR. We'll talk about NCR on the next section. So everybody find NPR in their calculator, punch in 10, NPR 4, and hit equals. And make sure you get 5,040. If not, let me know. You get it?
Mm-hmm. So wait, if you do the numbers out of order, is it still no? No.
Give you a different answer. Yeah, you can't do 4 NPR 10 because you can't choose 4 things 10 at a time. Right? There's only 4 to choose from, so you can't choose 10 out of 4. Great. Anybody not able to get 5,040? Let me know if you're not able to so we can look at your calculator. Everybody's good? Okay. So half the homework, guys, is just doing things like 10p4, 17p3. So you're just punching into your calculator. Now, going back to that other example, that tricky one, this guy right here, this would be 100p37. So this would be a royal pain in the butt, but what happens on the calculator? Well, now this is 100 NPR 37. That number, guys, is 4.707, etc. The E70 means times 10 to the 70th power. It's scientific notation. That means we have a 47 with 69 zeros after it. That is a rather large number. Anybody feel like doing a tree diagram for that? Yeah, you'd be there the rest of your life and you'd still never finish. Excuse me. So does everybody see how that works? So this is a new tool in our toolbox for doing counting. So you have tree diagrams, you have the fundamental counting principle, you guys have permutations and factorials. Now let me show you an application of factorials here. One of the applications of factorials is words, and I'm going to put words in quotes. If I take a word, if we take the word plate, one of the things they're going to ask you to do is take this and rearrange the letters and figure out how many different words in quotations we can make out of this. Now, when we say words in quotations, guys, every rearrangement we're considering a word. Whether or not it's an actual English word or any other language doesn't matter. Just a different rearrangement of the letters. So instead of P-L-A-T-E, maybe it's A-T-L-P-E. Even though that's not a word, we're going to count it as a word. So that's why I put words in quotes. Everybody got that? Okay? So the question is, how many ways can I do that? Well, there are 5 letters. We're going to use every letter once. And so I'm going to use my counting principle to do this. How many choices are there for the first letter? 5, and then, and then, and then, and then. And so this is going to be equal to 5 factorial. So in general, it's going to be the number of letters factorial. 5 factorial, 120. So there are 120 different quote-unquote words that we can make out of the letters in the word plate.
That's great.
You must be good at Scrabble.
Yeah, not too bad. I hold my own. All right. Now, here's the problem, guys. What happens, though, if we have a situation like this? Since you wanted me to use pizza, we'll use pizza. How many letters are there?
4.
There are 5 letters. I don't know which. There may be 4 different letters, but there are 5 letters there. So, it's 5 factorial, but there's a problem here, guys, and that is that 2 of the letters are the same. Which means that this 5 factorial would treat this, if I just reverse those 2 z's, if I call this z1 and z2, if I wrote it as pi z2 z1 a, sorry guys, I don't like these to look like 2's. Should that really count as a different word? No, it's spelled the same way. So just reversing 2 of the same letter, flip-flopping those, should not count as a new word. It's still spelled the same way. The problem is the 5 factorial, the number of letters factorial, is counting that as a different word. And so in order to get rid of that double counting or multiple counting, what we're going to do is we're going to divide out of that the repetitions factorial. So this is going to be 5 factorial divided by z is being repeated 2 times, and so we're going to divide that by 2 factorial. And so now instead of 120, we get 5 factorial divided by 2 factorial, which is going to be 60. So all those places where we could just flip-flop the z's, right, we've now divided those out. Since there's 2 ways to flip-flop those z's, right, to arrange those z's where only they change, there's only half as many as the 5 factorial. Everybody see how that works? What happens if you have something like this? Presses, how many letters? 7. So that's 7 factorial, but there are some repeats. How many e's are there? There's 3 e's. I only count 2. So we have to put a 2 factorial there, but notice there's also 3 s's, so we also have to put a 3 factorial on the bottom for the s's. Everybody see how that works? And so this is going to be equal to 7 factorial divided by, now we talked about this yesterday, be careful, I need the 2 factorial and the 3 factorial to be on the bottom, so I need to use parentheses. 2 factorial, 3 factorial. So now there are 420 different words, truly different words. Again, words in quotes, but where we're not just flip-flopping e's with e's or s's with s's. Right? We're not counting those multiple times. If we have 3 s's, guys, right? If we have an s number 1, an s number 2, and an s number 3, this 3 factorial is 3 times 2 times 1, which is what? What's 3 times 2 times 1? 6. Because I could have s number 1, then s number 2, then s number 3. I could have them in this order. Or I could have 1, 3, 2, or 2, 1, 3, or 2, 3, 1, or 3, 1, 2, or 3, 2, 1. Do you see that there are 6 different ways to arrange 3 s's, where I just changed the order on the s's? So we're counting that as 6 different words each time for each arrangement. So that's why we're dividing this 6 out with that 3 factorial right there. Does that make sense, everybody? So that's what the factorial is taking care of for us, is how many ways of rearranging just that one set of letters. Questions about that process? So that's the other type of problem you guys have on your homework tonight. Any questions? Great. Let me give you the assignment.